let's see, this is the data that I am plotting here. Both I am plotting here the mean velocity, which is your essentially u bar, and this is the urms. So this is actually RMS, it is okay. So urms is here. I am plotting both to the same scale here. That means they are non-dimensionalized by the same velocity. I am using the friction velocity or whatever inner velocity scale right now. So I have this u bar. U bar is this red dashed line, and the urms is this black continuous line. So away from the wall, so this is your not z, if I'm using y, right? Y here. Okay. So this is the wall, basically the wall direction here. Wall normal direction. So wall normal direction, and this becomes wall here. You are approaching the wall. So as you go away from the wall, you see that, let's say here, this is about the turbulence velocity here, urms is about, let's say 2, and at that same location, if I go up and I see the mean momentum is at least 10 times larger, an order of magnitude different. Therefore, away from the wall, where delta was the lateral length scale, the velocity scale for the turbulence urms was different compared to u bar, that is in the outer layer, right? So we used this outer turbulent boundary layer. In this zone, the black and the dashed lines are at least an order of magnitude different, 2 and this is like 12, right? Some, let's say 10 times larger, an order of magnitude. But I now come to a zone where eta w is important, the inner velocity, inner length scale, right? So let's say I come closer here, let's say at distance 0.1 or so. So then this is about 2, right? And then if I go up, or even I come much closer, let's say here, let's say 0.01 or 0.05 or very, very small zone. Then you can see here, if I take this distance very close, this and this value, same order of magnitude, right? So your urms or this u bar is of the same order of magnitude as urms here in this zone. So this is the zone of the inner turbulent boundary layer here, right? So the inner turbulent boundary layer zone. We actually don't know how small it is. I'm just only giving a value 0.01 or 0. We don't know. This depends on the Reynolds numbers that you are working with. But at least close to that, we can see from data that they are of the same order of magnitude, mean momentum and the turbulence velocity. Okay, so I choose the same scale. Convincing, right? Same scale now we are going to use for all the velocities, momentum as well as turbulence quantities. So we go back here, and therefore I have used uw both for u bar, its gradients, as well as the turbulence quantities. Okay, so now with this, of course, I can say, I can summarize what we learnt here. So close to the wall, it is u bar, dou u bar, as well as this turbulence quantities, and RMS terms will have same scale, that is uw. Okay, since very close to the wall, that is the inner layer, inner turbulent boundary layer, is inner turbulent boundary layer. Okay, they are of the same order of magnitude. They are of the same order of magnitude. So we'll start doing the analysis now, order of magnitude estimates using this. So now if I go back and look into the equation here, the equation on the top, the u momentum, I'll just do order of magnitude estimates. So I would get, for u bar I'm going to use order of magnitude estimates. Again, okay, if I do this, u bar is, let's take here, this is uw, dou u bar is also uw over L, the first term. The second term is v bar. Of course, for v bar we didn't do, but we can use the continuity equation again, right? So using continuity equation, I can say I have the dou u bar by dou x is dou v bar by dou y, right? Continuity equation. From that I can get the scale analysis as, this is uw, dou u bar is uw by L is this dou v bar, sorry, or v bar here, okay, v bar and changes in v bar, all this I am choosing a scale, let's call it a new scale there. This will be nothing but v bar scale here by, or not v bar, I would not call it, yeah, let's call it v bar because that is what we need in the u momentum equation. This is eta w. So this is the continuity equation, right? So I would get here v bar will be essentially uw eta w by L. Okay, this is the uw eta w by L. Okay, fine. Anything else I missed here? Yeah, this is the v bar. Okay, so this is the, this whole term is the v bar, the scale that we have taken there, and then I have dou u bar, which is uw by dou y is eta w. So this is the left hand side part. Okay, so the LHS term is this. Now we move to the RHS. Again, I keep the pressure term not participate here for the moment. Okay, I'll come back to that later. So I have the turbulent term, which is, this is uw square by L, and the other turbulent term is uw square by eta w, and then the two viscous terms, which is nu uw by L square, this is nu uw by eta w square. I simply introduce all the scales that we considered so far. Pressure, of course, we are not letting it participate. Now if I look here, what is the condition that we say? We say that eta w has to be much smaller than delta, and delta itself is much smaller than L, right? That is the thin boundary layer. Therefore eta w is much smaller than L. So the ratio of eta w by L, what will that be? Here eta w by L will be extremely small. Okay, but anyway, so we have, if I take out this eta w also, I can have this two terms removed, then the left hand side terms both are of the same order of magnitude, uw by L, uw by L. Now suddenly when you go very close to the wall, the LHS terms are same. Okay, there is no big brother, small brother. Both are now twins of the same order here. When you are inside eta W, the inner turbulent boundary layer. So we don't know on the left hand side which is the largest term, right? So on the LHS, like we can say no large term on the LHS. Both are of the same value. So, and the objective of this entire inner turbulent boundary layer is that to save at least one viscous term, right? So we will see, we'll start from there. Let's take the largest viscous term and see which term will balance. Anyway, on the left hand side, I don't have any term which is saying this is big. Okay, so this must be the smallest viscous term, right? In between these two, this is the the largest. This is the largest viscous term here. Because eta W is much smaller than L, right? And it is eta W square. So this has to be the largest viscous term, and this is the largest turbulence term. Simply because we have eta W is much smaller than L. So right, so eta W goes to denominator, means this becomes very large value, and this also becomes very large value. Okay, so these two are the biggest terms here. So if I want to save both the viscous term and the turbulence term, I will first see, let's divide the whole thing by the largest viscous term to save this, right? So I am going to say, to save at least one viscous term, let's divide throughout by the largest viscous term. If I do this, obviously the right hand side, that term will be 1 here if I am dividing it throughout. So let's do this here. So I have UW by L over eta UW by eta W 1 by eta W. Okay, the first term. So I would, these two terms goes away here, UW and UW, rest survives. Okay, and then the next term is same, which is essentially, if I rewrite this, I would get UW eta W by nu. So this is UW eta W by nu, and then eta W by L. Okay, both are same here, these two terms are same, the left hand side, right? So both will be the same, and question mark here. So this is UW by L over nu UW by eta W 1 by eta W. So if I do this, I get one of the UW's go away and the rest of the terms survive here. Yeah, actually this term, yeah, it's interesting here. You see, this particular term here is nothing but, its UW square is nothing but the same as the left hand side term, right? So this is also, I don't need to do this. So this is nothing but your UW by L, which is nothing but the left hand side term, right? So I would get the same here. So now we are seeing that the one of the turbulence term is also same as the left hand side acceleration terms. So I get the same uw eta w by nu and then eta w by L ratio. I have the other turbulent term, the second largest, sorry, the largest turbulence term, which is uw by eta w over nu uw by eta w 1 by eta w. Okay, so here this goes away, this goes away. Okay, and then the viscous term, which is nu uw over nu uw by eta w. So I would get, so it is eta w square by L square, which is extremely small because eta w is at least 2 orders of magnitude smaller. Let's imagine that delta is at least 1 order of magnitude less than small. Okay, so if L is, let's say, 10, delta is at least 1 and eta w is at least 0.1. So it is 10 times smaller than L. So eta w by L ratio will be very small, and this is square of that. Eta w square by L square is negligible. And then of course the last term, when I divide this is 1, of course. That is what we are trying to see, which term must balance here. So if I rewrite here, I would get, so this particular 3 terms are same here. All these 3 are of the same value and eta w by L is very small. Okay, so eta w by L is very small and therefore they are negligible here. All these terms are negligible, these 3 terms, eta w by L, and this particular term is eta w square by L square. Okay, so this is also, so I can say all these terms are second order importance, or you can say negligible here. This is negligible, it's also negligible term. This and the eta w by L whole square term also, this is also negligible here. Negligible. So it's very clear, if pressure term is not participating, or at least we are saying that is also not first order importance, inside the inner turbulent boundary layer, which term is balancing? 1. There is only one term here. Let's see what it looks like. So this particular term is uw eta w by nu. uw eta w by nu. Every term is negligible because it's a ratio of eta w by L, so very small, except this particular term. Now the largest viscous term is being balanced by the largest turbulence term. And what do we learn from this? What is this uw eta w by L? A Reynolds number of, based on what? An inner velocity and an inner length scale. Okay, an inner Reynolds number is 1. We are going to that close to the wall now. A local Reynolds number there inside the inner turbulent boundary layer. uw eta w is 1. Okay, so what did we learn here? To first order, the equation becomes your uw eta w by nu is 1. That is Re eta W is 1. Okay. This is to first order we have achieved inside, and the equation that is balancing, what is the inner equation that we have, is the largest turbulence term balancing the largest viscous term. Okay. So we will revisit this and then look in, are there more layers inside, because the pressure term we have to see whether that will also play a role. So we will revisit in the next class.